Okay, welcome back to another video lecture for a number theory series that will be posted over the next several weeks, hopefully. And in this video, we're going to be looking at some of the introductory part 1 elements for number theory, including the sets, some basic operations, and a proof technique of specific types of mathematical statements that will become very important as we go further into number theory. So number theory starts with the natural numbers. Those are numbers 1, 2, 3, 4, and so on, the counting numbers. We call these the natural numbers, and they are denoted by this double-barred N symbol here. The second set that is important to number theory is the integer set, and these are the natural numbers 1, 2, 3, 4, and their negatives, -1, -2, -3, so on. And also the number 0 is included in the integer set, and it is denoted by this double-barred Z. Now specifically, there are two groups that we're concerned with in the early parts of number theory. This is the, I guess I should say 4 groups. This is the natural numbers under addition, and the natural numbers under multiplication, and then furthermore the integers under addition and the integers under multiplication. So there are two operations that we're specifically concerned with, at least in the early parts of number theory. Now, one of the most important proof techniques in the beginning of number theory is the principle of mathematical induction. And mathematical induction is a statement, is a theorem that we will prove as soon as we've gone through the statement itself. And then we will use this in some examples going forward. So let's review what the statement actually says. The principle of mathematical induction says if we allow P of n, which is just some kind of mathematical statement, so this is like one thing equal to another. An example of this might be 1 plus 2 plus 3 plus and so on, all the way up to plus n, is equal to n plus 1 times n over 2 or something to that effect. And if we consider a statement like that, what you'll see is it's usually a statement of equality with the integer, specifically positive integer number n, being used somewhere in it. So that's what this first part of the statement says. It says P of n is some kind of statement, usually a statement of equality, and the little number n is drawn from our natural numbers. In other words, it's a positive integer. So mathematical induction says that if two conditions are met, then we will be able to show that the statement is always true for any value of n that we want. So the first condition says that if we can establish that P of 1, where we allow n to take the value of 1, and we can show that that is true, then we can build a basis for mathematical induction. And the second step says if we can show that for a k value, k being drawn from the natural numbers, that P of k being true implies that P of k plus 1 is also true, then that will mean that P of n is true for all possible values of n. So we set up this basis step, and the second condition is called the inductive step. And basically what we're doing here is we're choosing some arbitrary value k, and we're going to assume that the statement holds all the way up to k, and then it becomes our job to show that the statement also holds for k plus 1. And if you think of this like it's a sequence of dominoes, effectively what we're doing is we're showing that if we can knock over this first domino, P of 1, then it will knock over every other domino all the way down the line, so that we get that the statement is always true for every natural number. So going forward, we're going to begin with a very short proof for this, and then I will show you some examples using induction, and we will go forward from there. Okay, so to begin proving mathematical induction, we first need to bring an object into existence. And that object is this set, which will denote S, which is equal to the set of the natural numbers where P of n is true. In other words, this is all the possible things that I could plug into our given statement that will make it true. So first of all, because n, lowercase n, is being drawn from the natural numbers, we can make some observations. First of all, s must be some subset of the natural numbers. Okay? So secondly, we know that if we're going to be able to prove this with mathematical induction in the first place from the statement, we're going to have to be able to show that p of 1 is true, because if p of 1 is not true, then we can't use induction for this proof anyway. So what that gives us, because p of 1 is true, then 1 is in our set S. And now it should be stated that the goal here with this proof is to show that as we build up this set S, which is a subset of the natural numbers, that set must actually equal the natural numbers, and therefore our object, which we are using to show that a statement is true, S, in other words, all of the numbers that will make our statement true, happens to be all the natural numbers, and thus the proof. Okay, so for each n in the natural numbers, and notice we already have that 1 is in our set. So if I just kind of keep a running total over here, I've got this blue notation. This is going to be our set S. From the basis step, we already have that 1 is an element of our set. Otherwise, we won't be able to use induction on it at all. So for each n drawn from the natural numbers, what we will notice is that if n is an element of our set S, this is going to have to imply that n plus 1 must also be an element of our set S. That's our inductive step. So n being in S implies that n plus 1 must also be in S, and we will have to show that every time we go through an inductive proof. And what that's going to do for us, since for any natural number we can see that the next natural number is also in our set S, that's going to give us that the natural numbers is actually a subset of our set S. But if S is a subset of the natural numbers, and the natural numbers are a subset of S, then that's going to give us an equivalence relationship that the natural numbers are the same thing as our subset S. So since S is the set of numbers that make P of n true, if we can show that n implies that n plus 1 is also in S, thus making the set of natural numbers equal to S, then P of n must be true for all values of n. So here we have an example of what mathematical induction will look like when we use it to try to prove some statement. So here is the statement that we need to prove. It says that if you sum up the powers of x, so 1 plus x squared plus x to the third plus all the way up to some value x to the power n, it is the same thing as writing down x to the power n plus 1 minus 1 divided by x minus 1. And there's a couple important qualifiers here. First of all, we note that n cannot actually equal to 1, because if n equals to 1, then we have this division by x equals to 1 will give us that our denominator term here is a 0. I used n and I should have said x, excuse me. N can in fact be 1, because notice it just counts what the powers of x are, but x is not allowed to be equal to 1, because if x is equal to 1, then we have a division by 0, which we are not allowed to have. So first step in mathematical induction is to establish what we call the basis, that is that P of 1 is true. Now notice that when we look at the left-hand side, we have this long expansion here. Well, if n is equal to 1, then notice that's just 1 plus x to the power 1, which is actually just this part of that statement right there. So p of 1 will give us that we have 1 plus x on the left-hand side. On the right-hand side, what we will notice is that we have x to the power 1 plus 1 minus 1 over x minus 1, and I can probably do this one in a different color. Okay, so notice here that this actually gives us x squared minus 1 divided by x minus 1, which is easily manipulated to equaling x plus 1. And then through some quick commutativity here, we can rewrite this as 1 plus x, and you notice that the left-hand side is precisely equal to the right-hand side, so our basis step holds. Okay? So our next step here is what we call the inductive step. In the inductive step, we need to first assume that the statement holds all the way up to some value k, and remember k is a natural number. So that's like 1 plus x squared plus dot 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 all the way up to plus x to the power k should equal to x to the power k plus 1 minus 1 over x minus 1. And this is an assumption, so we are just going to say that this particular statement is true, and then it is our job to show that the statement holds for k plus 1. Okay. Now, k plus 1 would give us, if we go to the next term on the left-hand side, so for k plus 1, we have that 1 plus x squared plus dot 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 plus x to the power k plus x to the power k plus 1 should equal to. Now notice here that this portion of our statement that we're trying to show is the same as our assumption. So we can substitute this blue underlined stuff with x to the power k plus 1 minus 1 over x minus 1, and then we have this added little piece on the end where we're supposed to add x to the power k plus 1. Now here we have a common denominator situation where we are going to have to combine some like terms here. And so I'm going to just work with this right-hand side because we need to show that we will get something that looks in the same form as our original statement. Okay, so I'm going to come over here, and we have x to the power k plus 1 minus 1 over x minus 1 plus x to the power k plus 1. Notice here that the common denominator is x minus 1, and so if I multiply both things by x minus 1, what I will actually have is a large statement x to the power k plus 1 minus 1 plus, and then I'll have x minus 1 times x to the power k plus 1 all over x minus 1. Now, distributing through this thing very quickly, I want to point out a few things that are going to happen here. We're going to have x to the power k plus 1 times x, which is going to give us x to the power k plus 2. Okay? Then we're going to have x to the power k plus 1 times minus 1, which is going to give us minus x to the power k plus 1. And since we have minus x to the power k plus 1 and positive x to the power k plus 1, they're going to cancel each other, meaning the only thing left in the numerator is this minus 1 term here, which gives us this statement. And this looks pretty similar to what we're supposed to show, but remember we're supposed to show that basically if I replace this n with k plus 1, that we were able to arrive at that conclusion from our assumption step and from the basis case. So I need it to look almost exactly like this. It needs to say k plus 1 plus 1. And it turns out that's actually pretty easy to do. If I just replace this k plus 2 with k plus 1 plus 1, then you will notice that if I were to cover this k plus 1 up, this is the same thing. It's like saying x to the power n plus 1 minus 1 over x minus 1. We have shown at this point that we are able to arrive at the correct conclusion. And so what we finally need to write down here is that thus by mathematical induction, and usually we write this whole thing out, but I'm going to abbreviate here, P is true for all n drawn from the natural numbers n of the proof. Now here is